Marco. All right, so here you go. Worked out solutions. Here's the original set of parametric equations. And it said that you're supposed to show that you actually have two tangent lines that meet at 3, 0, right? Okay, so you can do this a couple of different ways. One of the ways is this is your x coordinate. So if you put that equal to your t squared and you solve that, you get two different times when your x coordinate is 3. If it hits an x coordinate at two different times, you're probably going to have two different tangent lines. Now we'll still have to find the slope there. And so I did go through the process of finding the slope. So when you do take the square root of that, of course, you get plus or minus the square root of 3 for your t value. You find your slope dy dx as the change in y over the change in x, or dy dt over dx dt. And then plug in your square root of 3, plug in your negative square root of 3, and you get a slope of plus or minus the square root of 3. Crazy. Okay. And then you already have your coordinate. The point was given to you as 3, 0. So one's a positive slope, and then one is the negative slope on that. All right. Now, if you don't eliminate the parameter, finding horizontal and vertical tangent lines is pretty easy, because all you got to do is take the derivative of this guy and set it equal to 0 for verticals. Take the derivative of this guy, set it equal to 0 for horizontals, and just make sure they're not the same, so we don't get 0 over 0. What would you have to do if you got 0 over 0? You'd have to do L'Hopital's rule. Yeah. All right. So let's say here is the horizontal one. So setting the derivative of y with respect to t equal to 0, you get plus or minus 1. I did say that you got to check the dy dt, so I checked that after I took its derivative, since I had to find the vertical tangent lines anyway. So you only have t values, but you usually want to know where these tangent lines occur. So I need xy coordinates. How do I get that?
Plug it in.
Yeah, you plug it back into your parametric equations back up here, right? All right, and then whenever you take the derivative of the x function and then set that thing equal to 0, it's just 0. That doesn't match up with either of the two horizontals, so you're good. And so again, you just plug that into your parametric equation, so you can see where you have that vertical tangent line. The slopes, yes, the t values don't match up, right? Okay. And then as far as concavity goes, you have to find the second derivative. So let me just scroll down so you can see what that second derivative looks like. The derivative with respect to t of the first derivative, you'll have to use the quotient rule on it, and then divide it by the derivative of x with respect to t, which we already found is 2t. Quotient rule happens, simplification happens. The top is always positive. You have a supercritical here at 0 over here. So that just means that if t is greater than 0, it's going to be concave up. If t is less than 0, it's going to be concave down. All right, we good? Kinda. Part A. Let me see if I can zoom out. I don't know how. Can you see it all right? All right, you ready for arc length? Good, let's hit it then. Time to think.
Yeah, just hold it
Here, I'll also do this. This will make it better. What's that? What did I bring? Oh yeah, that's right. We do need to take a mental break, but do we need it right now?
No,
Finish it? Yeah, we'll take it up.
I don't have to think about it.
We should finish the lesson.
Yeah,
and
I
then-
think we can do the lesson.
All right, let's punch it. Over here. So here's the graph for that. So notice that right there at 3 comma 0, there's where your two tangent lines, two different tangent lines that cross each other. So the graph, the plane curve actually crosses itself. Weird. And then there's also your two horizontal tangent lines. And did we have a vertical tangent line? At 0, which is not marked, but right over there. Okay, arc length. Does that arc length formula look familiar?
Yep.
All right, so we're just going to use that as a place to start, okay?
So we just changed that.
Yeah, so what are we going to put in the place of f prime of x?
DX. No, not the XCT. The T version of the Y over the T version of the X.
Yes, correct. Yes, that's exactly what we're going to do. So it looks like this. We do have to replace our, these are x values or whatever, so we have to replace them with t values over here. All right, so I just took out the f prime of x, replaced it with the Leibniz notation, and we said that that's dy dx is equal to dy dt over dx dt. So it looks like that. All right, now we're going to do some fancy algebra. That one that's over there, we're going to rewrite the one as a fancy one. Can you guess what the fancy one's going to be? Do you have the answers over there?
Yeah, I do.
Okay.
Why do you ask us to guess if you didn't think anyone would get it?
No, I wanted to know if anybody would be able to piece that together. Okay.
I do.
All right, then. Now, just going to rewrite them with the same denominator or common denominator. And we are taking the square root of this. So what happens down there in the bottom? Yeah, the square and the square root cancel each other out. And this is the weird thing that you get. You get that dx dt down in the denominator. But you already have a dx over there as part of your integral. What happens with all of that stuff?
Which part?
You have a dx out here already as part of your integral, but this whole entire integrand is being divided by dx dt. What happens?
Square.
It
No.
cancels out with the respect to x and the integral.
Oh, isn't it?
I didn't get that.
Yes. The dx dt the dx's, those differentials cancel out, but the dt is on the bottom of a fraction, which means it has to go back up to the top. And there you have it. So let's examine this arc length formula. It's actually pretty straightforward. You're taking the definite integral from your one t value to the other t value, square root of, and doesn't this sort of look like the the Pythagorean theorem?
Unfortunately.
Right? Unfortunately. Derivative with respect to t, a derivative of x with respect to t squared plus the derivative of y with respect to t squared. There's your arc length formula. Now it does put in an extra little bit here, and that's assuming that your curve is only transversed once. If we're talking about your t value, as t increases, let's say from 0 to 5, we want to make sure that it only goes over your curve, whatever it is, once. If it did, you have to make sure that you only do that part, or else you're going to double up on your perimeter, your arc length.
Parametric function.
James, you missed a little bit.
Yeah.
Don't worry, all the rest of this will be completely obvious.
Oh, yeah. Yeah, right.
All right, you got something down? Let's come back over to, I think it was this same exact equation here, this parametric set of equations. Let's find its arc length over the interval from 0 to 4 for the t's. Okay. What was our dx dt again? Dx dt?
2t minus 2.
dy dt?
1.
Okay, so now whenever I go to take the arc length, it should be equal to a definite integral from 0 to 4. Again, this sort of just looks like the distance formula here. I'm going to take the derivative of x with respect to t and square it, plus the derivative of y with respect to t squared, and take that integral with respect to t. All right, now as far as this one goes, you're not going to be able to find that one by hand because you're going to have a squared underneath that square root. So it's calculator time. If you leave it in parametric mode, you can still do it exactly the same way. It'll just have t's there instead of x's. Give it a try. How many decimal places do we go to? What do you get?
11.226.
That is correct. All right. Now, let's look at it in terms of just thinking of it as pieces of line segments. So if you take a look at the picture I've made here, I've just kind of broken it up into right triangles. And sure, this green curve is a little bit bigger than that red segment, but this is a good approximation just to make sense of this. Okay. So if I think of this as a right triangle, it's 1 by 1. What's the length of the hypotenuse right there? I'm going to demote you back down to algebra 1. Square root of 2. Okay, and this one is exactly the same, so we get another square root of 2. He did. Okay, this is 1, and let's see, that is 3 down here at the bottom. Root 10. This one is also 1, and it goes from here to here. That's 5, which is the square root of 26. So in your calculator, quickly just do square root of 2 plus square root of 2 plus square root of 10 plus the square root of 26.
It's a little less than 11.226. That's my guess.
Creating that found the arc length, but this was just a normal arc length.
We did. This is just like.
Oh, wait,
doing
no,
proofs
yeah,
on-
yeah. This is,
Yeah.
okay.
What'd you get about?
This is normal.
Yeah, it's pretty close to just being about 11, which is close to what we had. And like Sean said, our answer should have been a little bit smaller because we're using straight segments instead of curved ones. All right, why don't you go ahead and take out your memory card. Let's go ahead and write. See, we're on to the second objective, which is vector stuff. So we can write all the parametric stuff on it. Okay. All right, on the front side, you can see the parametric equations. We want what is the derivative of y with respect to x? What is its formula?
dy dt divided by dx dt.
Yes.
Yeah.
What is the second derivative?
dt of dy dx divided by dx dt.
Yes, you are. Now, remind me, what does this part up here, this d dt, mean that you're supposed to do?
With respect to the
Yeah. You take the first derivative that you had here and now take its derivative with respect to t, and then divide all of that by the derivative of x, the original thing, with respect to t. All right, and then we have one more here. We have our arc length formula. Definite integral from alpha to beta, we'll say. Square root of. Yeah. What goes inside?
dy dt squared plus dx squared.
I like my x's to go first. I'm gonna do my
Oh,
x's
okay.
first.
It's like segregation.
I'm just alphabetical that way. And then with respect to t. Whoops. Peyton would have said something.
What?
Now we're done with parametric.
Right, except for the lesson's not over. Do we need a break right here, though? Keep going? Let's go. All right. This brings us then to our second objective. Look at this guy. He's handsome.
Unlike us. We went. What?
You're not having fun
We're
right
having
now.
a blast.
All right, so the vector valued functions that we're going to talk about here is always in terms of motion. It's not rectilinear motion anymore. Now it is curvilinear motion. And so you're going to define your x component, your horizontal component, separately from your y component and put them together in a vector. What notation have you guys used for vectors in either pre-cal or in physics?
J and I think.
J and I?
Prefer X and Y.
I think we used.
Do you use chevrons?
Oh my God.
The pointy brackets?
Yeah, we did. We did the little corners.
Yeah. Okay.
Did we use like the column?
I don't think so. No, I did you guys use it to
Actually, I have.
where it looked like a matrix in pre-cal? Probably not, because I don't think they did matrices at all in pre-cal.
I have it in my house.
Okay.
Yeah, we have the columns actually.
Oh, you do?
Oh, you do? In physics or what?
No, this isn't pre-cal. This is the exact sheet we have. And then like J and I, VI, BJ.
Where's the stacked version? Yeah, where's the column? I don't think I see it.
Goodness. No idea anywhere. That's all we had. Yeah,
Yeah,
that's
magazine.
I had it.
Where can I get a parametric worksheet?
Oh,
Right there.
wonderful.
No. James. Geometry.
Okay.
It's over there. It's the stapled packets.
He's like, this worksheet's too hard.
Yeah.
It didn't work. It was like freaking.
Marco. All right. Curvilinear motion, particle motion defined in the coordinate plane, so that now instead of just being bound by an axis, either left, right, up, down, we can make some neat little curves whenever we throw our objects someplace. And we define your x's separately from your y's, your horizontal separately from your y's with respect to time. So think of it as doing exactly what we did before, just 2 times for a given problem. So when we were doing rectilinear motion, we only did horizontal or we did vertical. So now we're going to combine both of those together in one problem. So we have a horizontal component, we have a vertical component, so we can get motion in 2 dimensions instead of just 1. Oh, if only we can get motion in 3 dimensions.
No. I want motion in 4 dimensions.
Motion in 4? Well, you can generalize what we do here to 4 dimensions easily. What is it? What is it, Ethan? This is trivial. We'll leave this up to the viewer. Okay.
Let's see what rate that.
It's right. It's over here by Jake. All right. So we're going to ordinarily define these things as a vector valued function. So we're going to plug in a t value into this function, and it's going to spit out a vector. And that vector could be the vector for position. It could be a vector for velocity or for the acceleration. And so here are the components that you usually see. So here are the 2 most commonly used ones. Those pointy brackets, their special name is a chevron. Chevron. Yeah, the sharp parentheses. Don't cut yourself on them. Yeah. All right, so the domain is some real variable, usually time, t, but the output or the range is just a set of vectors. All right, so here is the chevron version of that. And Sean said that you guys have also used the I and the J version of it as well.
I actually don't remember.
I don't remember. It's because we didn't have to do it really. Mr. B made it like optional last year. Because
Which-
during COVID.
Yeah, which means that you were the only one that did it, Sean?
Yeah, probably.
Okay. I think a lot of us did it, but we just copied it down.
Oh, yeah.
Yeah, I'm over here like, what about? Easier to remember which one works.
Right?
Yeah.
Yeah. Well, it goes in alphabetical order for all of the stuff. So I before J, and yeah. All right, ready? So here's all of our calculus stuff. Here's all our particle motion stuff in terms of this vector that we've decided was our position vector. Okay. So the position function is this vector valued function. It's r of t. I plug in a t value. It's a time value. It's going to give me an x component and it's going to give me a y component that's determined as a function of time. So what do you think you got to do to find the velocity vector?
Again,
How?
based on time.
Yeah,
Oh,
and
the time derivative of each individual
that's right. It's so easy. It's the easiest thing we've done all day. It's just, you just do the derivative for the x's separately from the y's, put a comma between them, you're done. That's the position vector. Here's the velocity vector. How do you think you find the acceleration?
Do it again.
Yes, that's right. You just do it again. That'll come up here. Okay, so let's make sense of the speed. So speed is supposed to be absolute value of velocity. And since this is a vector, we usually say that as the magnitude. So if you think of, maybe I can draw it over here. We have a horizontal component, and then we also have a vertical component, but I want the absolute value, which is the magnitude, which is the distance from here to there, just the distance, not as a vector. How would you find that?
Hypotenuse.
Yeah, which is the Pythagorean theorem, which is exactly what that is, right? As a matter of fact, it was about the Pythagorean theorem too.
Yeah, James do that.
James do the parametric equation.
Yeah.
Now we know why.
Okay. Now, do you remember when we did total distance traveled? Total distance traveled was you take the definite integral of the speed function, right? So you just do the same thing here. So it's going to look just like we did the total distance before. And then finally, our acceleration vector. No funky business.
Wait, you put the interval?
Yeah, sometimes they will give you instead the velocity component, and then you'll have to work backwards by taking the antiderivative to find the position component. And sometimes they mix it up. They give you one position for x, and then for y, they give you the velocity. Like, why do you do that?
These are all going into our chart.
It will, yes. No.
I got a formula for it has calculus on there.
So how do you suppose that you would do the integration then?
Same way you do it with the.
That's right. You just do it individually. You do it for the x component separately from the y component.
Wait a minute, so. What?
It looks like this. So this is saying that f and g, those are like, we can say our velocity functions. So if you take the antiderivative of that, antiderivative, you can get the position x value, you can take the antiderivative of the g function to find the position. So like I said, everything is identical to what we did before. You just do it twice for the same exact problem. Once for x's, once for y's.
I need to see an example.
You want to see an example? I got you covered. Yeah. All right, so look at exercise 9. Particles moving along a curve in the xy plane is at a position x of x comma y of x at time t for t greater than or equal to 0. And look at our x component and our y component. If you have e to the t mixed in with all your stuff, chances are this is
E to the T.
calculator question.
That's also true.
So the very first thing that I'd like for you to do, we already set ours to parametric mode. So go to your parametric mode of your calculator, go to y equals, and then type in your x component and type in your y component. Maybe that lowercase t would look too much like a plus sign or something on my screen.
My graphics are screwed up.
You may have to change your t value. We want to start at t equals 0. And then just make your t max something large. Now, as far as, okay, that should be more than adequate. Yeah.
Does the X bend and stuff like that?
Yes.
Does the X bend and stuff like that?
So just use the graph grid that I have right here as a cheat sheet. So go from negative, it looks like -5 to +5 for x's. And it's probably -8 to +8 for your y's. Anybody get a graph yet? Yes, that's the shape. Yes. What? Marco. Now, if you watch it as it graphs, let's say, for example, this is on a calculator active question because it happens. If you watch it as it graphs it in order. So that would indicate the orientation for you. So it'll start with t equals 0 and keep going. All right. So now let's see the other stuff that we have to do. Part B, find the velocity vector and the acceleration vector at time t equals 1. It's going to be easy. Find the speed at t equals 3, and then the equation of the tangent line to the path of the particle at t equals 2. All right, here we go. So to find the velocity vector, we're going to take the derivative of each of the components. Very simple. It should be
-3 t squared plus 4 plus e to the t,
comma.
2t.
Okay, so there is the vector for the velocity function, but then it wants it just evaluated at t equals 1. So just plug a 1 in there.
So could you just plug that in and then do the derivative of the function?
Yes, you can. So now, no, you can't plug it in first. You have to take the derivative first and then plug it in.
If you don't put those like chevrons, does that make it wrong?
No, so it would be, it's kind of like a transcription, not a transcription error, like it's almost like a misspelling because you use the wrong notation for it. Is that safe stoppable?
Yes.
Yeah, it technically is, but you could do it. See, this would be a -3 plus 4. That's a 1. It's 1 plus e, comma 1. Okay. And then it also wants the acceleration vector. So for our acceleration vector, we just take the derivative again, which should be equal to
-6t plus e.
here we go, comma 2. All right, so plugging in 1 here should be even easier. -6, whoops, that was not pointy enough, times 1 plus e to the first power, comma 2, which is just e minus 6, I guess. Okay. If I'm not mistaken, you can still do this on your calculator. So I want you to see what it looks like on your calculator when you press, so go into your derivative, which I think is second math and number 8. And then inside of that, oh, first of all, you have to put a T down there in the box, right? Okay. And then inside of the parentheses, hit the second, no, alpha F4. And I think you should be able to choose separately your X component from your Y components. So you just have to do them individually.
Wait, I put alpha 4 and just gave me t. Is it second alpha 4?
No, it's just alpha F4.
I just got t.
Bring that over here.
What does your graph look like?
Oh, F4.
Really?
I got it.
Okay. All right, part C, find the speed at t equals 3. No, speed's not arc length, only total distance. Speed at 3.
It's only gonna change the acceleration.
So we're going to take the square root of, oh, actually here, I'll write it like this because we want it at 3. So v of 3, absolute value, square root of
dx so
-3.
t squared.
And I'll go ahead and, since we already have our derivatives right here, we can go ahead and just go ahead and plug in our 3's as we go, right? So -3 times 3 squared plus 4 plus e to the third power, all of that squared. Plus, and then do the same thing for the y's. This one's a little bit easier. 2 times 3 minus 1, all of that squared. It's just straight calculator.
Do we have to interpret any of these?
Sometimes, yeah.
Is it the same idea, but you just have to like take into account like the y?
Correct, yeah. Like, for example, when you take the derivative in a contextual problem, what did you just find? So it's like, oh, it's the rate of this is increasing or decreasing at, whatever. And then equation of the tangent line at t equals 2. How are we going to find the tangent line? Like, tangent line needs slope. So how are we going to find the slope?
You're just the same thing.
Isn't it parametric equations, essentially?
Yeah.
So then how do we find the derivative? Like, slope is always dy dx. So how do I find that for parametric equations? Correct. That's right. Which we already found here. So I'm just going to do it over here on the side so I don't have to keep flipping back and forth. So dy dx is equal to, we just take the quotient of these two things essentially. So 2t minus 1 over negative 3t squared plus 4 plus e to the t. And then you would want to evaluate that at t equals 2. It does say find the equation of the tangent line, so I'm not done yet. Go ahead and plug it in and let's get a slope here.
I should have put T, I mean, T is 2, right?
Correct, yeah. So if you wanted to do that in here, let me flip it over to the camera so we can just watch the whole thing happen.
And then argue how every time something goes wrong, you can also provide an argument.
All right. So we can do it from scratch on here, at least I do believe so. So we have the dt that's there, and inside of the parentheses here, I got to escape out of here so I can get inside of the parentheses. I need the dy dt over dx dt, and you have the y component and the x component stored in under y1, right? In here, right? Okay, so I'm going to set up a little fraction bar so I don't have to use all kinds of parentheses and stuff. That was alpha y equals, if you didn't know. And then I go alpha f4. What goes on top? Yeah, it's the dy, so it's going to be the y component on top, and then the x component on the bottom. So this is the slope of the tangent line at t equals. Wait, did I do that right? No, I didn't. Look what mistake I made.
Oh, you did what?
That need to have been an x. Okay, there we go. And then this one is at 3. There's our slope.
What was the other one?
Super steep. The other one was individually taking the slope or taking the derivative.
Oh, so you did that, and then you did another one with just
Correct.
y, and then
Yeah.
you just added those two together.
Yeah, as a vector.
As oh, not added that. Okay.
Was it at 2?
Yeah.
Oh my God, it's at 2. You know what? You know what?
Drastically different.
Yeah.
What? Just going from 2 to 3?
It's ridiculous.
All right, so here's what our slope is. Okay, but we still also need an x and a y component. Can you get that from the calculator screen?
Yeah.
Say yes, because you can. You go like this. You can graph it, or you just do it on the home screen like so. All right, so I hit alpha, y equals, let's get the x component. So I just do that, put in parentheses 2, hit enter, there's the x value. Okay, so I'm going to do it again. I'm just finding the x and the y coordinate, the original one. So I went alpha f4, not taking any derivative, just the original equation. Now I'm going to go down to 2 to find the y component. And in parentheses, it's just like function notation. Plug in a 2. And that one's a nice, neat -5. You have a slope. You have a point. You should be able to write your equation.
I guess I had another question.
Oh, yeah.
What? Are you getting different numbers? Maybe Joseph typed his in incorrectly.
Huh?
Wait, what'd you?
Okay, yeah, so this is the question I have. So when we find, like, this is for speed,
Yep.
if we were trying to do that for the t version, dt version, which is parametric, is the reason why it's square root of this square is because this is absolute value of the thing?
You can think of it like that, but do you remember the picture that I drew? Here is your horizontal velocity component. Here is your vertical velocity component. Absolute value is the magnitude of that. It's the distance between those 2 points. So here's your x distance, here's your y distance, and we'll call that one r. And it's just using the Pythagorean theorem, which you mentioned before, and then you got to take the square
How
root
did
of
we
it.
find it when we did it with this?
That you just find the velocity, take the absolute
How did
value,
we do that?
chop the sign off.
I don't remember how we did that.
You have a velocity function.
Yeah.
You plug your number in. If it's positive, you're done. If it's negative,
You make it
take the
positive.
negative off.
Oh.
That's it.
Wasn't
The
there a
reason-
way to make it into a function though?
What's that?
Wasn't there a way to make it into a function? Or do I just leave it absolute value?
You just have to leave it absolute value because that's what you have to do if you're finding the total distance traveled, and you have to integrate over that. And then that's when we broke it up over some sort of intervals where it crossed the x-axis.
And why does this absolute value equal this?
Because absolute value means distance from zero. So this right here is zero.
Oh, so that's
This is
zero,
the
and
origin.
that's where you end.
Yes.
So that's the distance from zero.
Yeah.
Okay, makes sense.
You want to see something pretty cool?
So it's like an actual
I don't know, I find the rate at which it's spinning.
Find the time delay.
Can you sketch that as a parametric curve?
Okay,
do a really hard job. Not a problem.
What did you guys see in the chat? Just people discussing how many people we have. Had the keyword.
all right, here's the next one. Let me see what that one is.
Yeah, can you show the answers to that one?
Which one?
The one we just did.
Oh, yeah, yeah. I thought we went through that one, didn't we? Where were you? This is right there.
Yeah, but you don't have like the exact values.
That is an exact value.
Oh, wait.
It actually is more of an exact.
Yeah.
This is true, but
Yeah. Now that one, it didn't work out because calculator.
okay.
Would have just thrown that into the calculator. And then D, we did on Joseph's calculator.
You just
Yeah.
0.7205.
Yeah, we did that. Yes, was that what it was? 0.702? Yeah. Yeah. Okay. All right, we'll do one more of these, I think, and then that will finish off the parametric part of this. We'll write some of that stuff up. I'll give you some time to take a look at that packet. There's some FRQ questions on there. There's some multiple choice questions, and then in a couple of hours, we'll see how much that we can do of polar stuff before we leave. Okay. All right, so particle moving along a curve in the XY plane. The reason why I want to do this one is because this one's backwards. Notice that we have essentially the velocity component of the X and the Y instead of the position. Okay. Find the speed of the particle at t equals 1, and then find the average speed of the particle over the interval from 1 to 4. That should be fun. Okay. You want to go ahead and throw those two in your calculator before we move on? And now just realize that these are, even though you're plugging them in for X and for Y, they're actually derivatives, okay?
You don't even have to go backwards.
That's right, I don't for that one. For none of them do I have to go backwards on. I have to go forwards on C. So occasionally they do ask you that they want, hey, what is the position at time t equals whatever? So then you do have to use an integral.
For the average, when we do
Definite integral, so it's 1 over b minus a, definite
over
integral.
A to B.
Yes,
Yeah,
Yes.
I thought we were using that, but I wasn't quite sure.
it's what it is. Okay, so let's first find the speed and speed at 1. So we'll find the speed equation first, I guess. So part A here.
Oh, wait, I didn't plug it.
It's just dy/t by j.
No, speed
Square root.
square root. So it's the it's Pythagorean theorem. And we already have our derivatives, which is pretty handy here. So it's just arctan e to the negative t squared plus, make that a little bit longer, 3t over 1 plus 4t cubed squared. And then wherever there's a t, you want to plug in. Now, Can you do that in the calculator with these two things plugged in for x1 and y1?
Yeah.
Yes, you can. No derivatives there, because there's no derivatives here, because we already have it. So we got a 1 there.
Oh, you just do the, like, the X and then.
Correct, that's right. And 1 cubed. So on your calculator screen, it would be start with the square root, and I would call up that x1t. I think that's what it looks like, right, for you guys? And then square it plus, and inside here, you just plug in an extra set of parentheses of 3 squared plus y1t of 3. Is it 3? It's not 3, it's 1. Come on. What you get, I'll tell you if you're right. That is correct.
I mean, 696. Right.
696, yeah. Okay. Now remember that if you do have to do calculus with the calculator on those free response questions, you still need to write some stuff down. Don't just put a calculator answer and be done with it. Okay, so now I want average speed from 1 to 4. 1 to 4? Yes, from 1 to 4. So I'm going to do that average value definite integral, which is 1 over 4 minus 1. That looks like 41. Try again. From definite integral from of the square root of
I just say absolute value of 0 over
just do this with your Apple Pencil.
Oh, I see.
Now I got to take these ones out and put t's back in their place. Easy. And then a dt there. Yeah, that one's definitely straight calculator.
How do you get that little pop-up menu with the bars?
Alpha F4.
I'm just gonna insert. Integral, I won't rewrite that.
Did you get a number?
0.209.
Yeah, I did not get that.
So close. You didn't get a number? You didn't get that one?
I did.
Okay, let's see what else it asks us to do. Find the distance traveled by the particle over the time interval from 1 to 2. Well, it's the integral of speed, and then the speed is the square root function, which is what we just did here. It's going to look just like this, but it's not going to have this in front of it, and the interval is going to be different. And again, just take your Apple Pencil on the calculus exam, just circle stuff, copy it and paste it.
Are we gonna be able to use this like we're taking it online?
No, I don't think so. So they're not, if you're taking it online, they don't let any, like you can't upload anything. So I want to say all free response questions must be typed. So they give you some math editor.
It's gonna take forever.
I would think so.
That's ridiculous.
I also agree with you.
Well, now.
Yeah, the digital version has all kinds of things against it.
justify it, except my submission didn't work.
What you get?
0.4077.
Yes, yes, and yes.
I have to retake it over the time. And I got.
Marco, all right, one last piece. Find the acceleration vector at time t equals 1.
Take the derivative of the velocity.
Yes. All right. So let's go ahead and find the derivatives like right here. So I want the second derivative of x with respect to time. So there's no chain rule here because they're already with respect to time. So its derivative is, you have to use chain rule on it.
One over.
We know it's.
No, yeah, well,
Negative.
one over one.
Yes, there you go. Negative e to the negative t. You can, yeah.
E to the negative t squared, q squared.
Now, I know from the last test that some people think that e to the negative t or to the t, whatever, squared is equal to e to the negative t squared power, but it's not. Power to a power, you multiply them, it's 2 times t. This should be negative 2t. All right, so there's that component. Oh, to find this component, that should be fun.
No.
We love the quotient rule. Y double prime is equal to derivative of the top, quick. 3 times the bottom.
14. Wait, no, yeah.
1 plus 4.
No, you don't take the derivative of both of them. Minus.
3t
Minus
t.
Oh, sure.
12t squared.
Right.
Over.
1 plus 4t cubed squared.
My God. Oh, yeah. And then when you're all done with all that, you still need to plug 1 in. But can you do that straight on the calculator?
Yes.
Yes, you can. So again, what you would do on your calculator is this part separately from that part, and you would do a d, like on your thing, it's d over dt, capital letter. Inside there, just call up your alpha f4, and inside here, that would be x1t. And then out here, it's t is equal to, what do we say, 1? And you would find the horizontal component and then do it separately for your vertical component.
When I asked you to find the vector, you represent an I and J factor. You represent as a.
Either one.
Could you represent as like a diagonal, like R hat?
I haven't seen it like that. I mean, I don't see a problem with you doing as a matrix. Chevrons or the IJ are the most commonly used ones. Not one that I've seen on the calculus exam for sure. Yeah. All right. Yeah, we're taking a bit of a break here.
Polar.
Yeah, polar. Oh, why did I take off my mouse?
Wait, let's write the green card stuff first.
No.
Yeah, I think we should take a little bit of a break.
Yeah.
And then, you know, with some space in between there, then write the stuff on there.
How long is the break?
How long should our break be?
3 minutes.
15. Sound good?
No,